Okay, so so let's briefly continue this. So because this is basically we have done now with model formation, and so we established that this is like this, and for fMRI, because that's what we're mainly interested in, that's for fMRI, that's a voxel MR. So of one voxel, the voxel MR time series, signal time series. Then we were here and we established that this is n times p, and this is predictor time series, so condition specific predictor time series or regressor, or columns of the design matrix, or the same thing, predictor time series. And these are of course created by convolution of the stimulus onset functions with the hemodynamic response function. So look again at this example that we looked at with the voxel, and put this in the context with the stuff that we discussed last time on convolution, because that's the same thing, only that last time we looked at the mathematics of this convolution operation, and before we looked at it more intuitively, stating that we have some stimulus onsets and we want to make a prediction of the MR signal. And then what is the beta? How many are there? Exactly. And what do they mean in terms of fMRI?
The weight for the predictors or
no. Yeah. And in terms of now really analyzing data, where do we get these parameters from? Yes, but how do we get, it's not really the amplitude, it's just the scaling of the entire regressor. So the entire regressor basically looks like something like this. And then, of course, this is all multiplied with 1 beta. So, for example, times 3. Then, of course, it's scaled. But where do we get the betas from?
You predict 1 beta, and then you form the differential of the whole equation, and then you always update the
yeah, that's but and how would you call this entire process?
Yeah, I forgot the name.
Yeah, so I mean we haven't really.
I think it's numerical.
Yeah, that would be. But what? How do you call this process of getting the betas? Well, we haven't discussed it yet, and that's really the topic for today. But it's model fitting or parameter fitting. And what you described is basically a numerical approach to it. So take start with an initial beta and then update that, for example, using Newton-Raphson, as we discussed last week in Statistics for Data Science. But one can actually do this analytically, and this is then the topic for today. So we want to estimate these parameters, and of course they are unknown. If you're doing data analysis and you want to obtain an estimate, unknown and estimate desired. And the main reason why we want an estimate for them is because they tell us how much each of the predictors, so each of our condition, contributes to the observed signal, and if that's a lot, then our condition modulates the signal quite a lot, and if this is 0, then our predictor has nothing to do with the signal. So that's the intuition from this example that we looked at. And then what is epsilon? And how is that distributed, maybe? Yeah, but
most of the time.
Well, the assumption is it's not so much how it is distributed in reality, but just in this model. So in this model, it's normally distributed according to a multivariate normal distribution. That's important, and it has a for what we're doing now, it has a spherical covariance matrix, meaning it's the identity matrix multiplied by a sigma parameter, which is the variance parameter of the GLM or noise parameter. And this parameter is also, of course, unknown. And it needs to be estimated. Anything? No. Good. Yeah, so this is really what you should have in mind all the time. I mean, the example is clear, but of course so the example in terms of fMRI, but of course, as we've seen earlier, of course, we cannot only model fMRI data with that, but we can also model other kinds of data that, for example, we want to explain with a linear regression model or some other data that we want to explain using a t-test or ANOVA. But of course, for what you are doing in principle, fMRI is the typical example that you should keep in mind. Good. So this is model formulation, and essentially we are now done with model formulation. Of course, a lot more time could be spent on talking about model formulation. Because, for example, we didn't discuss at all what good design matrices are. So how the regressor should be ideally formed, meaning how, for example, how in time you place your onsets and so on. There's stuff on that in the script, so one can go into much more depth in talking about model formulation, but for the moment we keep it at that. And now I want to talk about how to estimate the parameters. So basically go now to model estimation. So that's then the next big chunk to talk about. And we will, once we establish the maximum likelihood, we will also, I think, as a next thing, establish general least squares. And also then do REML, so we will go a little bit back and forth between making the model a little bit more complex by putting in error correlations so that we account for the fact that fMRI data is actually a time series, and the errors, so errors close together in time will be correlated, and model estimation. So today we do model estimation, and then we, for a couple of weeks, go back and forth between model formulation, model estimation, and then in the end, when we talk about random field theory, we will go to model evaluation. So the big topic then today is maximum likelihood estimation. Of beta and sigma square, because these are the two parameters that we want to estimate. And one thing you should always keep in mind about statistics in general, whether it's Bayesian or frequentist statistic, is how this thing about the world and the parameters and science and so works. So we did that briefly last week also in the other course. So the important thing is that in the world we assume that there are true but unknown parameters. And the parameters of a GLM are always the beta parameters and the variance parameter. And we assume that in the world, maybe we do them with a little tilde here, there is a fixed and true parameter value. so if we formulated our GLM, we assume that in the world now there's a real and fixed and true value for beta. For example, if there are 3 beta parameters, then these true values could be 2, 2, and 4. And then if there's always one variance parameter, so the variance parameter could be 1. And the assumption is that these parameter values via multiplication with the design matrix and by sampling from the multivariate Gaussian distribution gave rise to the observed data. And then let's say that this is our observed data here. The problem of science in general, and because statistics is science essentially, of course under the assumption that probability theory is a good thing, the problem then is of statistics and science that these true parameter values are unknown. Yeah? So we don't know them. If we would know them, then we already would know everything about the world, and somehow that doesn't seem to be the case. So they are assumed to be unknown. And the thing is, they also will remain unknown. We will not ever really learn them. What we can do is we can come up with, so in statistics or science, we use the observed data, so the time series of one voxel, to estimate the true but unknown values. And we estimate them, and this is what we will discuss today, with estimates, which we denote with this hat, so beta hat and sigma square hat. So these estimates are then our best guess for what the true but unknown parameters are, and these are the ones that we will report in a paper, and which we use to, for example, do hypothesis testing by computing a ratio between some beta parameter estimates and variance parameter estimates. But all of this is basically using transformation of the data to get to these estimates, but these will always be just estimates, and the true but unknown parameters will remain unknown. Of course, if you simulate all of this, then you can, in your simulation, set true but unknown parameters, sample data, and compute estimates, and then look at how good your estimates are with respect to the true but unknown parameters. You can not only do this in simulation, you can also do this in your head, so analytically, and then discuss the qualities of estimators. That's actually the topic in statistics for data science for the next 2 weeks, I think. A general principle to come up with estimates is maximum likelihood. So does anyone of you know what maximum likelihood is about? And what is roughly then?
You try to say how likely your model is given the data you have.
No, that is not, in a way, I mean, it's connected somehow with parameter estimation, but to say how likely the model is, not really. So, what is the idea of maximum likelihood estimation? Anyone else?
Choosing parameters which are most likely to your data.
Now what? I mean, it's going into the right direction, but it's not quite there. So you want to use a parameter as estimates that maximize something, but what do they maximize?
Function.
Yeah, but what does this function mean? Anyone else? So the idea of maximum likelihood is that you choose parameter values such that the observed data under your model and these parameter estimates becomes maximal. And this can be formalized in terms of the likelihood function. So when we now want to introduce maximum likelihood estimation in the GLM, first thing we need is the likelihood function. Then we need to know what a maximum likelihood estimate is. And then we need to know how to find them. So we introduce maximizing the log likelihood function, I guess. And I think I want to do this in parallel. So we first always introduce the abstract concept, and then we immediately apply this to the GLM, so that you always have the example with you. Maximizing the likelihood function. So the general idea is of a likelihood function that first of all you have a probabilistic model. So you have you have a probability distribution over some data. Yeah? So that's what I call a probabilistic model. And y here is the data, and theta is some parameter. And it's important to note that this probability distribution over the data is parameterized by theta. It's not conditioned on theta. This would be a Bayesian scenario where the parameters are also conceived as random variables. Here, the parameters are not random variables, and hence they are not conditioned on. So what is the probabilistic model in terms of the GLM? Does anyone remember? We looked at that also previously. So obviously we wrote down the structural form of the GLM above, but if we talk about the probability of the data, which we now need to talk about, what is the probability of the data in terms of the GLM? What's the or we can also say what is the probability density function of the data in the GLM context? We looked at that previously. So if you want to turn this into a statement about the probability distribution, so the whole thing, not only the epsilon, if we want to turn this into a probability statement about the data, what is this probability statement? What does the formula that we look at there say about the distribution of the data? No? Is it exponentially distributed, the data, or is the data Bernoulli distributed? Yeah, but about the probability distribution about the data. It's normally distributed, yeah. It's and is it a univariate Gaussian or multivariate Gaussian? Multivariate. And what are the parameters of a multivariate Gaussian?
So the covariance matrix.
So let's maybe So there's a covariance matrix parameter, and there's what?
The X or
Now, what is the other parameter of a multivariate Gaussian? The covariance matrix parameter is one, and then there's another parameter. Yeah, exactly. And so mu is the expectation parameter, and sigma is the covariance matrix parameter. And now for the case of the GLM, what are mu and sigma?
mu is the design matrix times
And the covariance matrix?
the errors.
Yeah, but what is the covariance matrix then of the data? So it's not the epsilon, obviously.
The distance for each data point?
No. So basically what we have established so far is that for the GLM, the let me put it down here, for GLM, the probability distribution over the data is a multivariate normal over these. So this is when I write probability densities, I put the y in there, and we establish also that the expectation parameter is x beta, and then the last thing is the covariance matrix parameter. It has to do something with the error, but the covariance matrix parameter of the data distribution is not the errors, but the covariance matrix of the errors. So that's sigma square IN. So that's the probabilistic model in terms of looking at the distribution of the data for the GLM. Yeah? So this is a general concept here, and for the GLN as an example, we see that the probability density function of the data is a multivariate normal distribution with this expectation and this covariance matrix parameter. So I think we discussed that like 3 weeks ago or something. And again, what are the parameters of, so here we have this theta, so what do we have in the GLM? What are the parameters in the GLM? Well, I mean, we discussed it just briefly some time ago. So these are the beta and the sigma square. Yeah? So the theta, so the parameters of the GLM are the beta parameters and the sigma square parameters. So that's now our probabilistic model for the data, which of course derives from this representation of the GLM, as we discussed actually previously. Good, so that's the first thing that we need. If we want to do maximum likelihood, we need a probabilistic model, we need a probability distribution over the data. And the next thing that we then need is the so-called likelihood function. If we want to do maximum likelihood estimation, and now the likelihood function, one way to write this is as follows. It's a function from parameter space to the non-negative real numbers, and it allocates to each value in parameter space, allocates one value, and this value is defined as the probability of data given a specific parameter setting. And that's quite important and also a little bit confusing because what you see here is of course the probability of data given a parameter setting, and so far we are used to looking at this as a function of the data. Obviously the y is in brackets, so it seems to be a function of the data. And now the crucial step you need to make in your head to go to maximum likelihood estimation is that you view the data as fixed. Yeah, so this is why there's the subscript here. So the data is fixed, and you view this probability of a specific data point, if you want, y here, or data vector, as a function of the parameter. Yeah, so you vary this theta, and this is why the theta is here an argument, and the whole likelihood function is a function of the parameter. Yeah, but the value it takes on at a fixed data point, and for a fixed parameter value is just the probability of the data given or under that parameter value. Yeah? Maybe let's do two more things before we go to stating this for the GLN. The first thing is in terms of maximum likelihood estimation, what we now want is a value of the parameter that maximizes the likelihood. It maximizes the likelihood function. So we want to find some parameter value in the parameter space big theta, such that the likelihood is maximal. Yeah? That's the way to write it. So you look for an argument of this function, hence the argmax, in parameter space, such that this is maximal. You always need to view this for fixed y. So for one observed data set, you shift around the parameter so that the probability of the observed data becomes maximal. Yeah?
Isn't that a proof that when you minimize the L2 norm of the shows that it's the same as maximizing the other norm?
Well, I mean, yeah, if you look into the script, so I think what you are referring. So I'm not quite sure what you mean by. Also, I mean what I know what an L2 norm is, but I don't quite sure what you mean by minimizing the L2 norm. Maybe you mean.
Loss function.
Yeah, maybe it means something like ordinarily squares. Yeah, so ordinarily squares and maximum likelihood for the Gaussian, but only for the Gaussian, are the same thing. And this is actually also somewhere in the script. The thing is, ordinarily squares is not a probabilistic way of finding parameters. So that's basically you minimize errors, but you just the aim is just to minimize errors, and you're not trying to. You don't view the data under a probabilistic model. And there are many loss functions. I mean, you can come up with many loss functions and many also regularization terms in there. But that's usually then a bit theory-free and more heuristically motivated. And yeah, so you can view maximum likelihood estimation for the Gaussian as the same as ordinary least squares estimation. The problem is if you only view things as ordinary least squares estimation, you will not understand, or there's no way to understand why, for example, where the t-distribution or the chi-square distribution then come from, because they come from these explicit probabilistic assumptions about the data, which are not in the ordinary least squares framework. Yeah, other questions about this so far? No. Yeah, so that's the maximum likelihood estimate, and maybe, yeah, what this then means is that one needs to yeah, somehow work with this function and find a way to maximize it. And what did you learn how to maximize functions in school? What do you do when you were supposed to find the maximum of a function?
Set the first derivative to 0.
Yeah, and Yeah, and
Has to go to 0.
yeah, and check.
I
What,
check for the second derivative is the maximum or minimum.
yeah, what do you check with the second derivative?
If it's not 0.
Yeah, and when is it a maximum?
If it's smaller than 0, it's a maximum.
Yep. Yeah, exactly. So the thing is with maximum likelihood estimation, usually just just computing the derivative and setting to 0 is essentially enough to find maximum likelihood estimates. Or at least that's the impression you get if you read statistics books, because they hardly go into the second derivative. One reason for that is that these functions that we're dealing with are often concave, so that they actually have a unique maximum. So the good news is essentially for us, we will only compute the first derivative and set to 0 and then solve. So essentially, if one formalizes this a little bit, what we want to do for maximum likelihood estimation is to compute the derivative of the likelihood function and look at this from the perspective of the necessary condition for an extremum, usually a maximum. Basically, if there is, in terms of the necessary condition, if there is a maximum at theta equal to this theta hat ml, then the first derivative of the likelihood function is 0. And this, if you use a numerical approach, you can of course use the same thing as for example, convergence criterion. So you can always, if you have some way to evaluate the derivative of the likelihood function, you can always check for your current parameter estimates, is the derivative of the likelihood function 0? If it's not, then you might want to go somewhere else. But if it is, then you know that you're at the location of a maximum or potentially minimum or potentially a saddle point, but then most of the time, because these functions have this property that they actually have a maximum, if you are in these kind of classical examples, then you will be at a maximum. And then there's one more thing that is often done, that instead of dealing with the likelihood function, so instead of dealing with Ly, one deals with the log likelihood function. So let's comment on this. So that's the necessary condition for an extremum. And then the last thing to introduce is the log likelihood function, which we can do quite quickly. So the log likelihood function is also a function of the parameters. It maps into the entire real numbers, because if you have, if you remember how the log looks like this. So this is 1. So you see that the log of the positive numbers actually can be both negative and positive, so it's a real number, and it assigns to each parameter, it assigns the log, so the natural logarithm of the likelihood function, which is the same of course as the log of the probability of the data at the location of theta. And the reason for using the log likelihood is essentially that it simplifies things, specifically if things are independent, then it turns, the log of course turns products into sums. Another thing is that it stretches out this bit, where if you are dealing with probabilities instead of probability densities, a lot of things are, so it makes this space a little bit bigger. And of course it doesn't change the location of a maximum or minimum because it's a monotone function. So whenever it takes on a larger value, then also the input value is larger than some other value, meaning that the location of the maximum is conserved under the log. And that's then what you usually would deal with in a practical setting. So instead of maximizing the likelihood function, you would maximize the log likelihood function. And for the calculations that we will do, we will also maximize the log likelihood function. Good, so these are the abstract concepts. So that's kind of this bit here. That's abstract maximum likelihood estimation. And now let's have a look at the case for the GLM. So let's first write down the likelihood function for the GLM. So GLM likelihood function. Because we want to use this, of course, to get parameter estimates for our model. So remember the GLM in terms of its probability model or probabilistic model looks like this: multivariate Gaussian, expectation parameter, and oops, sorry, and I should do this. So expectation parameter. We get there. Beta and covariance parameter. Okay, so the GLM likelihood function. So we will call this L, because why not? It's just a likelihood function. But the first question is, what is the parameter space? So the theta of the GLM. So can we say a little bit more about theta? So what are the parameters of the GLM again? Exactly, it's actually the variance. Beta again is what in terms of its mathematical? Yeah, but in terms of its mathematical. Yeah, but what kind of vector?
The dimension? P?
Yeah. So we definitely, because beta is a vector, we have the parameter space is definitely the p-dimensional real vectors. And what about the variance parameter? What can we say about this? So can it be negative? No. So what we always wrote is the because also the Gaussian is only defined if sigma square is larger than 0. This also implies it's a little bit weird, but it implies also something on the dimensionality of sigma square. So what is sigma square? Is it a vector? Is it a matrix? Is it a scalar? So what kind of values can you assign to sigma square? Can you assign vector values to it? So think about what this statement is supposed to mean, or think about
identity.
Yeah, that's the identity.
Right? Well, I'm not sure. I thought it's a vector, but
no,
probably it's a scalar.
It's a scalar. Yeah, one can. I mean, there are, and we will later see that you can come up with more complex error covariance matrix vectors. But in this case, it's really just a scalar multiplied with the identity matrix, which goes back to the fact that the errors are independent. So that was like 3 weeks or 4 weeks back. So the sigma square is a positive real number, So our entire parameter space is then the p-dimensional real vector space where the values of beta lie times, so all possible p-dimensional vectors times all possible positive real numbers. Yeah? And so that's our theta. Let's just take this up here. And this gets allocated actually in this case, because we're dealing with the probability density and we're dealing with the Gaussian, a strictly positive number. And then the question is, of course, how this is defined. So y gets allocated sorry. This was completely wrong. Now I cannot even erase it. What's going on? Sorry, that was completely wrong. So of course we assign to our parameters. That's why we established a parameter space in the first place. So our beta, and to a sigma square we assign a value of the likelihood function. And what is this now? If you look again how the likelihood function is defined. The Gaussian, exactly. So here we put this, and this is of course in our case the multivariate Gaussian. And then we can, of course, we now want to somehow shift around or somehow find a beta in a sigma square that maximizes this. So we want to, for example, essentially what we want is we want this. So a tuple of this, which is given as maximizer over parameter space. So this is what we want, and as I also explained earlier, we do this in terms of the log, because we do that because it makes so one thing that it definitely makes easier is that here we have the exponential function in the Gaussian, as you know, and if we apply the log to that, we get rid of the exponential, which is good because then things get simpler. So we just say we work with the log, and this then is basically what we want to get. So here we have the log likelihood function, which is the log of p beta square y, which is the log of n y x beta sigma square in. And this is, I think, as far as I wanted to get, because I think then we can continue here. Yeah. Yeah. Good. Questions up to this point?
I have a question just about your notation. The identity matrix, is it a mu or an n? Because it's n dimension.
Yeah, it's n. That's my n. Looks a little weird. That's my n. Yeah. Anything else? No. So the next thing that we of course need to do is, if we now want to find the maximum likelihood estimate for this and this, we have to basically use this first derivative setting to 0 rule. So we have to put in the probability density function here, compute the derivatives, which is not completely trivial because our beta is a vector and it's not just a scalar. We will be able to deal with it and then solve that, and that's what we want to do in the next hour. Yeah? So let's have a break and continue at 9. So 10 minutes break.